Hello everyone, welcome back to the video lectures on image and speech processing. So we have been talking for the last few videos about the image compression models. Like we have talked about what are the various we talked about various compression models that are existing. Like we have air lossless and lossy. In lossless, we talked about Huffman, Shannon, Fanon coding, LZW coding, arithmetic coding, right? And we talked about block transform, JPEG coding, right? So all these transform techniques were used for achieving the image compressions. So we would see for in today's video lecture the problems on the compression methods by which that are existing in this topic, and we will try to solve them using the various methods, right? So let's go for the first problem. We have a 4-syllable source which is A, B, C, D, and it have the probabilities of 0.1, 0.4, 0.3, and 0.2, right? And we are trying to sequence the code. We are going to encode the code of the sequence, which is BBADC, using the arithmetic code, right? So using the arithmetic coding technique, we are trying to solve this sequence. We are trying to code this sequence. So how do we do this arithmetic coding? Just we just erase this. Yes. So how are we doing it? We divide the range 0 to 1, right? So we divide this range 0 to 1 sequence by number of subgroups, right? So how many subgroups? They are divided based on the number of source symbols, right? So we have to divide this 0 to 1 into 4 subgroups because we have 4 sub symbols. So symbol sources, so we are going to divide it, and those lengths are given by the probabilities, right? So the length of that subgroup is equal to my probability. So how do I do this? So my first symbol is A, so its probability is 0.1. So the first subgroup is of length 0.1, right? Next comes your B, which is having my value as subgroup length to be 0.4. So 0.4 plus 0.1, which will be 0.5. Right? So C is having the probability of 0.3. So I will have this value as 0.8. Right? 0.8, next symbol is probability is 0.2. So it will be 0.2 plus 0.2, 0.8 plus 0.2, which is equal to 1. So this is my A, B, and C. Right? Now, my first sequence is B. So I'll be considering this sequence. So I have my sequence value as 0.1 to 0.5, right? Now I'm going to divide it again into subgroups based on number of source symbols, right? So how do I get these values as? How do I get this values as? I will take this value as 0.1 plus 0.1. What is the total length? Which is equal to 0.4 length into, what is this? Probability of my A symbol is 0.1. So this I'll get it as 0.14. So this is 0.14. Next symbol will be 0.14 plus 0.4 into, what is my probability value, which is equal to 0.4. So this is equal to 0.14 plus 0.16, which is equal to 0.3, right? So that is equal to my 0.3 values. Next is given by 0.3 plus 0.4 into 0.3. So that is equal to 0.42, right? 0.42. Now what is the next symbol value? I'll get it as 0.42 plus 0.4 into 0.3, so 0.2, right? So that I'll get it as 0.5. So this is my values. So this is A, B, C, D. Now my next symbol is B. So I will consider this range, which is equal to 0.4 to 0.3, right? So I will continue here. The values are 0.14 to 0.3. Now I am dividing it again into 4 subgroups. So that values are given by 0.14 plus, what is my length of here? 0.14 to 0.3, it is equal to 0.4, right? What will be the length here? 0.4 into, what is my probability of my first symbol? It is equal to 0.1, right? So that is equal to 0.18. 0.18 plus 0.4 into 0.4 is this is equal to 0.18 into 0.16 is equal to what is the value now? So what is this length here right now? I have 0.14 and 0.3. So what is this length now? Which is equal to 0.26, right? 0.26. So I have the length as 0.26. So I can get this values as 0.14 plus 0.26 into 0.1, which is equal to 166, right? So 0.166. Then I have 0.166 plus 0.26 into 0.4, right? So what will I get some value as, which is equal to 0.24, some value, right? Next, I have the value 0.24 plus 0.26 into 0.3, right? So I get this value as, say suppose I get this value to be 0.28. Okay. Now this is A, B, C, D, right? So we have coded A in the first step, B. Next symbol we have coded to the value to be B. Next we have the symbol A. So we have to talk about this. We will take this area or the subgroup next. So this is equal to 0.14 plus into 0.166. So that we are going to divide it again into subgroups, which is having A, B, C, D, right? So I am coding A, then I have to code my D symbol. So I'll be taking this range, right? So I'll be taking this range, which I'll calculate, and here I have A, B, C, D again, right? So using this, now my last symbol which I have to code is C. So this code C. So this range of symbols values which I am having, those values I am going to say that BBADC is coded using by this range of symbols or this range of values using my arithmetic coding, right? So basically in arithmetic coding we have 0 to 1 ratio, and that we are dividing into subgroups based on the number of code symbols we have, symbol source symbols. Then we are going to calculate the subgroup length based on my probability, right? So once I have coded divided based on my first symbol in my sequence, I am going to continue this process. So this is my arithmetic coding technique, right? So let's go for the next one. We have a next question is like, we have a symbol source which is having 6 symbols and they have their frequencies, right? So this is the source frequencies. Now we have to code using this Huffman coding, and we will calculate the compression ratio and the redundancy. So how do you calculate the probability when a question of this sort is given? So how do you do is, you first calculate the total number of pixels that are existing. Total number of pixels, right? So that is equal to 45 plus 13 plus 12 plus 16 plus 9 plus 5, right? So 45 plus 13 plus 12 plus 16 plus 9 plus 5. So this will come up to be 100, right? So now your probability of each source symbol can be written as, 45 by 100. Next, 13 by 100, 12 by 100, 16 by 100, 9 by 100, 5 by 100. So this is your, first we are trying to calculate what is the total number of pixels. Then this is the source symbol, source frequencies, right? So this is basically in your if you talk about in terms of histogram, it is like unnormalized histogram. So we are trying to calculate the normalized histogram, which is equal to the probability of the symbol. So that can be calculated by your unnormalized histogram by the total number of pixels, right? So we have got it to be 45 by 100, so on and so forth. Now this is equal to 0.45, 0.13, 0.12, 0.16, 0.09 and 0.05, right? So this is your sequence of your probabilities. Now when we have to go for Huffman coding, we have to arrange the probabilities in my decreasing order. If we observe here, it is we have to rearrange this symbols accordingly. So let me just write this table, which is equal to symbol probability, right? So what is your first symbol? I get the symbol as A, right, which is equal to, this probability is equal to 0.45. Next, which is the highest value, which is equal to 0.16. That value is for D symbol. So I have the symbol D, which is equal to 0.16. Next comes your 0.13. So that is equal to the symbol B, which is equal to 0.13. Next comes your C symbol, which is equal to 0.12. Right? Next is your E symbol, which is equal to 0.09. Your F symbol, which is equal to 0.05. Right? So this is how you rearrange your probabilities in your decreasing order. So in the next step, what do? You add your last two symbols. So this is, after adding, you try to rearrange your order again. If they are in your decreasing order, then they are left as it is. If they are not, we have to rearrange it, right? So this 0.45, 0.16, this will turn up to the, after the adding, it is turning up to 0.14. So after adding, it will go here 0.14, 0.13, 0.12. Right? So next we will add these two symbols, which is turning up to 0.25. So it will go up to here 0.45, 0.25, 0.16, 0.14. Right? So next we will add these two symbols. This is adding up to 0.30. So this we will arrange it as 0.45, 0.3 and 0.25. Right? Next we will add these two. We will get the addition as 0.55. So this is equal to, we are dividing it in this range. Right? So if we add, this is turning up to be 1. So based on that, this is my last stage. First stage, second stage. This is my first stage. This is my second stage. This is my third stage. And this is my fourth stage. Fifth stage is turning up to be 1. So this is final, the forward for Huffman coding, forward steps in my Huffman coding. So when we are going, we have to code the symbols, means we have to go back, right? So that is the backward Huffman steps. So how do we do it? The highest probability value now, it is 0.55 in my last stage. So that value I am giving it to be 0. Or for simplicity, we can even use 1. Okay. Now 0.45 is given the code value 0. Now when I'm going for my previous stage, I shift the symbols by 1 bit towards my left. So that is equal to, now this 0.45 is left as it is, because we have not obtained it by adding some other digits. So this 0.45 will have a single digit 0. Now 0.55 is having 1, which is obtained by adding 0.3 and 0.25. So when I'm trying to code it, what am I doing is I'm shifting it by 1 bit towards. So using that, I'll get the 0.3 code value as 10. And this is 11. Right? Now, when I go back to my previous stage, let me just erase it here. Now, so 0.45 is obtained as it is. Right? Now, 0.3. How did I get my 0.3? By adding this 0.16 and 0.14. Right? So that values 0.25 is left as it is. So I can take it to be 11 here. Now 0.3 I have obtained it by adding 2 digits. So that I am shifting it to my one side left. So this I am getting it as 101. and this I'll get it as 1 0 0, right? So this is my symbol. Next, this 0.16 and 0.14 are obtained as it is. 0.45 is also obtained as it is. So let me just erase it. So this value is 0, 0.16 is 101, 0.4 is 100, 0.3 is 0.13, and 0.12 should be obtained from 0.25. So that is equal to 111 and 110. Right? So this is your symbol. Now your 0.14 is obtained by adding 0.09 and 0.05. So let me just erase it here. So this value you have added, right? The rest of the values, which is 0.25, that is 0. Your code symbol is 0. 0.16, the code symbol is 101. 0.13, the code symbol is 111, right? 0.12 is 110. This 0.09 and 0.05 will be obtained by adding this, by shifting this. So that is equal to 1001, 1000. So this is your code. Every symbol is coded now. So A is coded to be 0, D is coded to be 101, 101, B is coded for 111, C is coded to be 110, E is coded 1001, F is coded for 1000. Right? So let me just go on here. I'll write the symbol and the code word. Right? So let's just write it. So what is this? We have these code symbols A, B, C, D, E, F. Right? So what is this code word? A is equal to, the code word is 0. Right? Next, how we have the code symbol B, that is coded to be 111. So that we are writing it to be 111. Now I have my C. How am I writing my C value, which is equal to 110? So 110. Now what is my D? D is 101. So that symbol is 101. Now if I have my E, that is given by 1001. Right? So that is equal to 1001. F is like 140, 3 zeros, right? 1000. So what is the code length now? Code length 1 3 3 3 4 4. So if you observe here, it is a variable length coding. So the Huffman coding, we are doing the variable length coding. Now, what is the second part? We have done the coding. We have obtained the code symbols using the Huffman coding. Now we have to calculate the compression ratio and the redundancies, right? So when we are trying to calculate the compression ratio, we have to assume that what is my highest probability that is existing, which is equal to 0.45. So how many bits do I require to represent it? Say suppose if I have the fixed length, I have to use 4 bits. Okay. Now using my, so when I use my fixed length to be 4 bits, my L average is 4 bits. So using 4 bits, I cannot represent all the symbols. I have to use 8 bits only. I have to represent 8 bits, right? So using this L average, when you use your fixed length, it will be 8 bits. Now when we are using this variable length, what will be my L average? L average is equal to summation of probability into your code length. Probability into your code length, which is given by probability of this A symbol is 0.5. Let me just add a probability column here, which is 0.45, right? 0.45, 0.13, 0.12, right? So your D is 0.16. This is 0.95, 0.05. So this is equal to 0.45 into code length is 1 plus 0.13 into 3 plus 0.12 into 3 plus 0.16 into 3 plus 0.09 into 4 plus 0.05 into 4. So this will be your L average. So after you calculate your L average, you can calculate your compression ratio by what is the fixed number of bits, L 8 bits, and your variable length. Based on that, you can calculate, right? So B by B dash. What is your average length? So this average length by this. So this is equal to your L by L average of V. So Halfman coding. Let me just write it as L average by Halfman coding. So this will be your compression ratio. What will be your redundancy? Is equal to 1 by 1 by C. So this is how we can calculate the compression ratio and the redundance value. Right? So next, the next problem is on LW coding. Right? So we have this LW coding, we have this image, right? So this LW coding is used basically for reducing our spatial redundancies. So how do we create? We create a dictionary, right? So in the dictionary, the first number of we are using a 8-bit. We are using a 8-bit code. Then we have the 0 to 255 values like predefined on the intensity values. Now if we for the LW coding, we will use 9-bit, right? So from 256 to till 521, 525, we have the dictionary to be vacant. So there we will go on adding. So what was the table? How do we write it as? We code it as the previous pixel. Let me just first, the pixel that we are going to consider in the first step, the previous pixel. If we have any value, then the encode output, the dictionary new entry, and dictionary value. So you have table, you create your table in this way. When you consider your first pixel value, which is 127, do you have your previous pixels, which is previous? We don't have anything. So this is 0. So already 127 is already existing in our dictionary. So the encode output is hyphen. There is no dictionary new entry. We leave it as it is. Right. Next, we will take the symbol 127. Right. What is your previous pixel which we have not coded? It is equal to 127. Now what will be your coded output? It will be actually 127, which is your previous pixel. Right. So that is equal to your previous pixel. Now, do we have this combination of 127 hyphen 127? No. So that we can add it to be as new dictionary entry, right? So that we can add it to be 127 hyphen 127, and the new dictionary value or the encode output value, we can put this value, the sequence 127 hyphen 127 in my new dictionary place, which is equal to 256, right? I can write it in the place 256. Now, next, let's go for the next sequence, right, which is equal to 127. What is the previous pixels that I have to encode? That is equal to 127. Thus is the combination 127 hyphen 127 existing. Just now we coded it and we have added in my dictionary. So that is equal to 256, the encode output. So we need not, it's already exist in the dictionary, so we will just neglect it. Next, we will take the symbol again, which is equal to 127. Now, what is my previous pixel which I have to code is 127 hyphen 127. Now, what will be my encode output? This encode output, it is equal to my dictionary value of 127 hyphen 127, which is equal to 256. Right? Now, do I have this combination of 127 hyphen 127 hyphen 127? It's a new dictionary entry, so I'm adding it to the 127 hyphen 127 hyphen 127, and this value I'm writing it at 257, which is a vacant position. Right? Now, let's go to my next value, which is equal to 25. So what is the value that I have, pixel which I have to encode now, which is equal to 127. So what will be my encode output? It will be 127, because this is the pixel which we are trying to encode, right? Do I have the combination of 25 hyphen 127? No. So I am writing it in my new dictionary entry 25 hyphen 127 at my 258 position. Now, Next, the value is 25. So the symbol which I have to encode is 25. My output will be 25. And 25-25 is a new entry. So I'm writing it as 25-25, which I'm writing it as 259 position. Now I have to take my next 25 value. So this is equal to 25, and my next pixel value is, or my previous pixel is 25. So this combination is already existing. So I'm writing it to be hyphen, right? So next pixel I'm going to take, which is equal to, next pixel I'm taking to be 25, right? So this 25 hyphen 25 combination I have to code, and that value is equal to 50 to 59, right? And I have the new sequence which is equal to 25 hyphen 25 hyphen 25. So that I'm adding it to be 260, right? So on we will consider the each pixel values, right? So next I will take the 25, which is having like 25 hyphen 25. That combination is already existing, so we will neglect. We will go again to the next symbol, which is 25. So that is again like 25 hyphen 25 25, which is already existing, 260. So we take the next symbol, which is equal to 127. So that combination doesn't exist. We add it in the new dictionary value and we try to code it. So what is happening here is the combination of this 127, if it is existing in multiple positions, though all these three pixels are coded by this one single dictionary value or the one symbol. So here, instead of using this 8 bits for 3, which is equal to 8 into 3, 24 bits, what am I doing? I am combining all these 3 pixels to be 1 pixel, and that is equal to 256. That I am coding using my 8 bits. So that is how I am able to achieve my compression using my LZW coding technique. Okay, so this process will continue. Now, let's take another example, which is where we are using the Shano-Fano coding method, right? Here we have the probabilities that are existing and the code symbols. So how do you do? This is very similar to your Huffman coding. We arrange it in my decreasing order. So I will write this table as symbol and my probability, right? If I observe my probability, I have to arrange in decreasing order. So I can write it as M1, which is equal to 0.3. Next, M2, which is equal to 0.25. Next is M3, which is equal to 0.15. Next comes your M4, which is equal to 0.12. Next is your M6, which is equal to your 0.10. Next comes your M5, which is equal to 0.08. Right? Now we divide it into 2 subgroups such that my probabilities of my upper half is very similar to my lower half. So what is this? If I try to do is, this is 0.5, 0.55. So this combination will give me 0.27. This is equal to 0.27 plus 10, which is 0.37 plus 0.08. This is equal to 0.45. Right? So this is the maximum closest that we can achieve. So I'll divide it in this form, right? So the upper half, whatever I have, the upper half which I have, that I am writing it to be 0, coding it to be 0, and this I am coding it to be 1, right? So the next stage, I'll divide it again this into subgroups, right? So I'll write it as upper half is 0, 0, and the lower half is 1, 0, right? This I have and divided into 2 subgroups. So how do I do is 0.15, 0.12, 0.18, right? So if I do it, this is equal to 0.27 and 0.18. So instead of that, if I use, I can divide it in this form, right? So how do I do is, this I write it as 1, 0, and this is this is equal to 1, 0, and this is 1, 1, right? Now, so this again I'll subdivide it into 1, 0, 0, and this will become 1, 0, 1, and this, when I'm dividing it further, I'll get it as 1, 0, 0, and this is 1, 0, 1, 1, 1, 1. So if I see, all my code values are 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 111 So this is how we go on for Shannon-Fano coding. We take the probabilities in my decreasing order. We divide it into two subgroups so that I get my probabilities addition are closest. Right? So I've divided into two subgroups in my first stage. Then that subgroup I'll divide it in my next stage into subgroups, so on till such that all the symbols are in individual subgroups. So this is, if we observe here, we are using different code length words for different probabilities. So this is also a variable length coding, right? Now, this is the run length which we have studied. So this is your run length image. This is mostly using for your primary image, which are having either 1 or zeros. So we are going to compress this using my run length coding technique. So how do I do? I write down my run vectors. So what are my run vectors? How do I write? The intensity value and the number of intensity values in that row. So what will be my value? I will write the value as 1, which is having 1, right? So this is 1. Next vector will be 0 and 1. Next vector is 1 and 2, right? So the next vector is 1, 1 and 0, which is 3. So your second row can be written as in this form. Now the next is 1 is having 2 length and 0 is having 2 length, right? The next is 1 is having 2 length. So the 1 is having length and 0 is having the length 0. So this is your run length vectors for your image, right? So based on this, the total number of vectors are equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are 9. Now to code each intensity, each vector, how many bits do we require for each vector? Each vector, if I have to calculate, what is the maximum length? 3. So how many bits are required to represent 3? I require 2, right? So how many bits I require to represent the intensity value, which is 1 or 0? I require 1. So I require 3. So total number of bits to represent image is equal to 9 into 3, which is equal to 27. Here I have 4 into 4, right, which is equal to 16. So this is how I can apply my run length coding technique to achieve my image compression. Right? So for the different compression models for different models, we can see using in this textbook, which is your digital image processing Gonzalez, where different examples and different models are explained in detail. Right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.